Welcome, my name is Philippe Verzuijp and this webcast accompanies my book Data Analysis. In it I will show you how to estimate an equation in eViews. If we have imported our data into eViews, then we'll see a work file with various series in it. Now each of these series contain a single variable and we want to estimate a regression with those. We want to make sure that there is something we explain, our dependent variable, with one or more independent variables. Now suppose that I want to explain the returns on a certain investment portfolio. Big BM3 is one of those portfolios in this dataset. And I want to explain this return by using three independent variables. Returns on a market, denoted M, HML, the high minus low factor, this is based on research in finance by Pharma and French, and SMB, the same, small minus big. Doesn't really matter too much what these things represent right now. So these three are our independent variables. Now, if we want to estimate this big BM3 as a regression with those three variables, we can do this in two different ways. First of all, the easy way. Secondly, I'll show you the slightly more laborious way, but a way which gives you much more control. The easy way is first to select all your variables, then right-click, open as equation. And then you will see that you get a new screen titled Equation Estimation. Now you need to be careful here. Why? The reason is that the first variable that's mentioned is always taken to be the dependent one, so the thing you want to explain. I want to explain big BM3, not M. So what we need to do is cut this and paste it at the front. Separate each variable by a space. You also see at the end that there is a C. Now this C stands for the constant. You always want to include that in the equation. Now with this small adjustment made, we just press OK and we get a regression. Over here we see dependent variable big in BM3 and several variables which each produce a coefficient. The constant does so as well. Standard errors to indicate reliability of those coefficients, t-statistics, p-values, and so on and so forth. There will be a separate webcast about the interpretation of all these outputs. Now this was the quick and dirty way. There's also another way to do this. If you go to Quick, Estimate Equation, you'll get the same screen. However, what we can also do in this screen is type out the exact equation we want in the syntax that eViews understands. So once again, first the dependent variable, but then we add an equality sign, and then C1 with the one within parentheses, plus C2 times M plus C3 times HML plus C4 times SMB. Now M, HML and SMB are, as always in this webcast, are independent variables. C1, 2, 3 and 4 are the coefficients we're going to estimate. And C1 stands for the constant, C2 the slope coefficient for M, C3 the slope coefficient for HML, and so on. This will produce exactly the same result as we had earlier. However, if we have a more complex equation, such would be the case when we are using dummy variables, this particular format is more advisable because it gives you complete control. It's almost impossible to get the wrong equation with this as long as you type out the syntax correctly. Once we press OK, we get the result. Now, we see an interesting feature of eViews, namely that every time you estimate an equation, it overwrites the previous one. In order to prevent this, we need to save these equations. There will be a new object in our work file. To do this, we have to click on Name, not Store, but Name. eViews will then prompt you to provide a name. Standard it goes equation 0, 1 and so on. That will work just fine. And you will see that over here in the work file there is an additional object titled equation 1. Now we have the new equation, which if we name it would be equation 2, which is the same thing, only estimated in a different way. The resultant statistic could be pretty much additional anything. Advantage of this over here we see values ranging from exact equation used up to 87. The customary cutoff point is last bit if never include in below 2 the formula for your equation bigger than minus 2, because so none negative values mirror the positive ones, you will see a probability value which is bigger than 5%. Now, this last column, this probability or p-values, will help you make the decision whether or not a variable is significant. If the p-value is below 5%, there is less than 5% chance that we find a coefficient of this size, while the true value would be 0. In other words, if the null hypothesis that the variable would be insignificant would be true, we would be highly unlikely to find these results. Therefore, we reject the null hypothesis. So, if the p-value is below 5%, the variable and its associated coefficient are significant. If the p-value is above 5%, we do not reject the null hypothesis, so the coefficient could just as well be 0, and therefore it is called insignificant. And therefore always also seen as a redundant variable which just as well might be removed from the model. It should be noted that the lower the coefficient, so the closer it is to 0, the easier it will be for a given standard error to produce a very low t-statistic. It's hard to distinguish coefficients which are very low from their value of 0. Unless, of course, the standard error is very low as well. Now, here you see that the coefficients move from values a little over 1 to a little over 1%, but that the standard errors are all in the same order of magnitude. So therefore we get different t-statistics, and therefore we can say that some variables are in this case quite good, and some variables are not as good. C4, the S&P in this case is not significant, could just as well be dropped.